In this video, I'll be discussing clock skew, which is an important factor to consider when designing robust and reliable digital systems. We will explore what clock skew is, what causes clock skew, the effects of positive and negative clock skew, and what are the design techniques to minimize it. So let's get started. First, what is clock skew? In digital systems, there are millions of flip flops on a chip, all of which receive a clock signal as an input. For the circuit to function correctly, each flip flop must meet timing requirements such as setup and hold times. If you would like to refresh your understanding of setup and hold time requirements, feel free to check out my earlier video where I explain these concepts in detail. You can find the link to that video in the description below. In any chip, the clock signal enters through the input port or pin and propagates through the circuit, eventually reaching the clock input of each of these millions of flops. Some flops are located close to the clock input port, while others are farther away. As a result, the time it takes for the clock signal to travel from the input port to each flop varies. This means that the same clock edge can arrive at different flops at slightly different times, depending on the path it takes through the circuit. Theoretically, the time a clock signal takes to propagate from the chip's clock input port to the clock input of the flip flop is called clock latency. So we can say that different flip flops in the design have different latencies for the clock signal. Now let's define clock skew. Clock skew is the difference of the clock latencies between the capture flop and the launch flop. Or in the other words, it is the difference of the time between the same edge of the clock signal arriving at the capture flop and the launch flop. Just a quick reminder, a launch flop is the flip flop that outputs data that needs to be captured by another flip flop. The capture flop is the flip flop that receives and stores data from the launch flop. For correct operation, the capture flip flop must meet its setup and hold requirements to ensure that the data is stored reliably and without errors. In the diagram shown over here, we have a circuit with two flip flops. Consider a flip flop FF0 as a launch flop and FF1 as capture flop. If we assume FF0 has a latency of LT1 and FF1 has a latency of LT2, the clock skew is LT2 minus LT1. The path with latency LT1 contains two inverters, while the path with latency LT2 contains three inverters. If each of the inverter in the design has a delay of 5 nanosecond, LT1 is 10 nanosecond and LT2 is 15 nanosecond. The clock skew between these two flip-flops is 15 minus 10, that is 5 nanoseconds. These are the waveforms of the launch clock and the capture clock. The clock skew, that is LT2 minus LT1, is highlighted in the gray color. Clock skew can be positive or negative. A clock skew is defined as positive if the capture flop clock latency is more than the launch flop clock latency. In this example, we have a positive skew if LT2 is greater than LT1. Clock skew is negative when the clock latency at the launch flop is more than the clock latency of the capture flop. That is, when LT1 is more than LT2. Now let's understand how positive and negative clock skews affect the setup and hold time requirements in a design. First, the positive clock skew. Positive clock skew is generally beneficial for setup timing. In the setup time requirement, the data launched at the launch clock edge must be available before the active clock edge minus the setup time at the capture flop. Here, the active clock edge is shown in the dotted black line. As we see, the active clock edge in the capture flop is delayed relative to the launch clock edge. This provides additional time for the data to travel from the launch flop to the capture flop. This helps the data to meet the setup time requirement and get correctly latched at the capture flop. Positive skew is beneficial for setup timing. However, it can be problematic for the hold timing. In case of positive skew, the active clock edge in the capture flop is delayed, and if in this case the combinational logic delay is short, the data may arrive at the capture flop too early, before the delayed clock edge. This too early arrival of data can cause new data to override the previously stored data, leading to hold time violation. On the contrary to positive skew, negative skew is good for hold timing and bad for setup timing. First, let's see hold timing. In case of negative skew, the launch clock edge is delayed relative to the capture clock edge. This delay means that the previous data remains stable for a longer period of time, giving the capture flip-flop enough time to reliably latch the data. As a result, negative skew helps in meeting hold time requirements. However, at the same time, negative skew can be harmful for setup timing. Since the launch clock edge is delayed, there is now less time available for the data to propagate from the launch flop to the capture flop. This time is now the delayed clock edge of the launch flop to the active edge of the capture flop minus the setup time. This reduction in the available time shortens the time window for the useful work to be performed in the combinational logic. Further, it limits the maximum clock frequency the design can support and impacts overall performance. Now let's discuss what factors contribute to clock skew. At high level, there are primary two reasons: the length of the interconnect wire and the delay in the interconnect wire. Let's find out how the length of the interconnect wire can affect clock skew. In a digital circuit, the paths taken by the clock signal to reach the launch flop and the capture flop can differ in the length. If one path has longer interconnect wire than the other, the clock signal will take more time to propagate, causing the same clock edge to arrive at the two flops at different times, leading to clock skew. In many cases, even when the interconnect wire lengths are identical, clock skew can occur. This is often due to variations in the wire parasitics, such as resistance, capacitance, and inductance, or inductive coupling from neighboring signal lines. Additionally, temperature fluctuations, process variations, and material defects can vary signal propagation delays. As semiconductor technology continues to shrink, these factors become increasingly significant, making clock skew variations more pronounced. In order to minimize clock skew in digital circuits, several techniques are employed during the design process. One of the most widely used and effective methods is the implementation of balanced clock distribution tree, also known as clock tree. It is a hierarchical network that distributes the clock signal to all sequential elements across the chip. The goal is to ensure that the clock signal reaches to all the elements simultaneously or with minimal delay variation, thereby reducing clock skew. To achieve this, buffers and inverters of various drive strengths are strategically inserted along the clock paths. These components help balance delays, compensate for parasitic effects, and align clock arrival times across the circuit. There are specifically designed clock buffer cells available in the standard cell library for this purpose. The ultimate objective is to minimize clock skew so that all related flip-flops are clocked as synchronously as possible, preventing setup and hold violations. Implementing a clock distribution tree in the design is known as clock tree synthesis in ASIC design flow. Clock tree synthesis is typically performed during the physical design phase after logic synthesis and placement, but before routing. It is executed using industry standard EDA tools provided by companies like Synopsys and Cadence. As the number of transistors on the ICs continue to grow, reaching into the billions, clock tree synthesis becomes an increasingly critical and time-consuming step in the design process. That's all for this video. I hope it helped you to understand what clock skew is, the various sources which cause it, its impact on the timing requirements, and the various techniques to mitigate it.